Okay, domain. Denominator can't be 0. This factors into x minus 7, x plus 2, can't be 0. X can't be 7, x can't be negative 2. So it's all real numbers except for 7 and negative 2. That says I have two VAs. And yes, it would be unpleasant to graph, but they're predictable. They're x equals 7, x equal negative 2. So now when I go to do my graph, I put a vertical line at 7. I'll put a vertical line at negative 2. And I'd be working my graph around those two vertical lines. And what's the end behavior model? End behavior model is x cubed, over x squared, which is x. X to the 1. This is degree 1, because x is not in the denominator, it's in the numerator, and that means I have an OA. It's oblique. Now the question is, how do I find it? If you had something nice, you could use synthetic division, but we don't have something nice. You're going to divide x squared minus 5x minus 14 into x cubed minus 1. X cubed plus 0x squared plus 0x, I've lost it already, plus 1. What do I multiply x by to get x squared? You'd say x, or x cubed. X times x squared is x cubed. X times minus 5x minus 5x squared. X times minus 14 is minus 14x. Subtract, which changes the signs. X cubes drop, plus 5x squared plus 14x plus 1. What do I multiply x by to get 5x squared? You'd say plus 5. So I'd have 5x squared minus 25x minus 70. Subtract, that changes the sign. And I come down with 11x plus 71. So essentially, the OA is this guy right here. The OA is the quotient, which is x plus 5. And then you might say to yourself, and you may have more room, and because I am out of it, and what I should do for this section, either break these problems up into two, so make myself a note, move to next page. So I've got room to write down here. So if I pull a piece of paper, you might say, well, why is that the case? Well, remember in all of this, if I were to look at this division, we're now saying this is x plus 5, and then I have a remainder plus 11x plus 71 divided by the divisor, which is x squared minus 5x minus 14. So when I did the division here, it left me with this as my quotient. this is my remainder. And what I'm saying is we can ignore this. And you're going to say, well, why? As x goes to infinity, what am I going to end up having? My model is 11x over x squared, because as x is very, very large, who's in control? The power functions are, which is 11 over x, which goes to 11 over infinity, and 11 over infinity, for all intents and purposes, is what? 0. So as x goes to infinity, this whole thing here goes to 0. And what I'm left with is x plus 5. So when I'm finding the OA, I have to do a division, denominator into numerator, and the quotient is what my OA is. This stuff doesn't matter, because as x gets very, very large, this whole thing goes to 0 and evaporates away.
So once you have your x plus a constant, you're good?
You're done. You're good. And that means if I'm finding an OA, if I'm finding a quadratic end behavior model, or not end behavior model, finding a quadratic asymptote, a cubic asymptote, they're all done the same way. Once you hit the OA, degree 1, you've got to divide the denominator into the numerator in order to find what it is. So what's the domain? Well, we know that 4x minus 1 can't be 0, which means that 4x can't be 1, or x can't be 1/4. So it's going to be all real numbers except for 1/4. That means my VA is x equal 1/4. The end behavior model is 8x squared over 4x is the quotient of the highest powers, which ends up being 2x. This is degree 1. So I have an OA, so it's oblique. Now what do I have to do? I have to divide 4x minus 1 into 8x squared plus 26x minus 7 to find the OA. This is 2x. 2x times 4x is 8x squared. 2x times minus 1 is minus 2x. Then you subtract, which changes the signs. X squareds drop, and I'm going to get a 28x minus 7. What do I multiply 4x by to get 28x? You would say plus 7. So this is 28x. Uh-oh. And in this case, I say, I have a problem. And you say, well, why? The remainder is 0. Well, your OA is 2x plus 7. Well, yeah. That's not what the problem is going to end up being. What the problem is going to end up being is this guy doesn't have a VA. And you're going to say, why is that? The reason for that is that 8x squared plus 26x minus 7 over 4x minus 1 can be written as over 4x minus 1. This is going to be 4x minus 1 times 2x plus 7. I would have never thunk it. 4x minus 1 reduces out. So this guy really is 2x plus 7. But the problem is, x still can't be 1/4. But I'm telling you, it's not a VA. Now wait a minute, x can't be 1/4, but it's not a VA. It is something else. At x equal 1/4, there is a hole in the graph. So that says if I were to graph this guy at 1/4, this graph looks like that. It doesn't have a VA at all. It looks like that. So I have to X this out and say none. And by the way, you can get caught up on that very, very rapidly. Good news is that's a calculus issue more than it is an issue here. It does have a name, however, that what we have here is something called a removable singularity. A removable singularity. In other words, I can remove the problem. I can remove the problem. So that says if I were to clear graph uh, 8x² plus 26x minus 7, and I forgot to put parentheses in, so I need to insert parenthesis divided by parenthesis 4x minus 1. You will not see anything that's got a VA in it. I'm going to do a zoom standard or zoom 6 to bring it up. It looks like a straight line. See, if I were to have a VA, and I'm just going to do something, I'm going to change that to a +1. That puts a VA at negative 1/4. If it had a VA, it would look something more like that. It would break the graph up. But that's not what it did. And by the way, depending upon what day it is, what year it is, what time it is, I could get caught on one of these if I'm not careful. I didn't look at the obvious, not obvious. That factorization isn't obvious. Now, if I were to now hit trace, and this is another way you can tell, and I'm going to type in 1/4 that I think my VA is. I'm going to put x equal 1/4. Notice, what do you see for y? Nothing. That's because there's a hole in the graph right at that point. There's no y value there. There's just a hole. That, for those of you taking calculus, you're going to run into that much more frequently there than you will here.